Hey, okay, welcome to our last video lab here in our electromagnetics, and we've been doing a lot of stuff on electromagnetics, and I'm sure that you're feeling it and maybe looking forward to wrapping this up. But our last lab is titled the RLC circuit. It's the last one in the lab manual. But I am going to make a couple of changes, and so I'm going to send out a PDF. I kind of rewrote it. It's not much different than the one that was sent to you, but it is a little different. And so as I send this link of the video, I'm also going to send a new PDF here of that. And this is, of course, material of chapter 33. This is our AC circuits. Let's talk about them for a moment, and then we'll hook it up and take our measurements. And I'm going to come over here and give myself plenty of whiteboard space. I don't know if really I'll need it. It's not a real big lab here. But let me start with our AC power source, and so this is the symbol we've been learning. This is going to put out an AC voltage. And what we're going to do is we're going to feed that to an inductor. And so there's the L part of our circuit. We're also going to feed it in series with a capacitor. So there's the C part, and then we will feed this to a resistor, and so there's the R part. Okay, so one of the things that hopefully you learned in chapter 33, and that we'll hopefully see here as we do the lab when we have our LCR circuit driven by an AC source, that is the current will be the voltage divided by the impedance. Now, as we start to make our measurements, we will measure the, and I believe it's peak to peak. I was going to put maximum, but I don't think that's true. Let me check the instructions here. Yeah, peak to peak. All right. Which means then if we divide this by the impedance, we should get the current as measured peak to peak. All right. Now what I really want to focus on, if you didn't catch it in the lecture, is this denominator here. And so for our experiment today, you're asked to set the peak to peak voltage at 8 volts. And because it can change throughout the experiment, you're asked every time you go to take data, look first before you write anything down, that the peak to peak voltage is set at 8. And if it is not, then we'll make some adjustments until it is. That way, we know that we are always delivering the same amount of voltage to the circuit. Because an important lesson of this chapter, and what we're hopefully going to see here in the lab, is that the impedance, which is all the pieces that are opposing the current, and in this case it is not only the resistor but the inductor and the capacitor, and they depend upon frequency. So we called this the reactance. And so this is saying here that how much current you get depends not only on how much voltage you give it, and I think that's obvious, and that's why we're going to leave it at 8 the whole time. We're never going to change that. That's so obvious that we don't want to see that effect. What we want to see is the effect of what we refer to as resonance. That is, what frequency are we at? Because if you were to think about this and make a plot, and so here is the current at different frequencies. If you have a very low frequency, you can see here that this term right here, the term that's part of the capacitor, becomes very big. And of course, when you have a big number in the denominator, you get a small amount of current. So maybe in this area of the graph where the frequency is low, we would get very little current. And then, of course, the other extreme is when you're at a really high frequency. At a really high frequency, this one is the big one. That one kind of goes away, and if this is really big compared to that, we can just kind of ignore that. But the point is, this is really big, and so again, we have a big number in the denominator, so we don't get much current. So on a graph, I might say over here, where the frequencies are high, I would get very little current. And so the reason we call this a frequency selector is it is selecting a frequency. Really, it's kind of a range of frequencies. But near the transition, where these two are pretty close to being equal, and in fact, when they are exactly equal, let's talk about that. But near this transition, these two balance each other off, and the only thing you have is this V divided by R. And so that magical frequency, maybe I'll put it right here, would result in a lot of current. And so coming up from the low frequencies to this magical frequency, it will build up. And then as we get frequencies greater than this magical frequency, it tapers down. And of course, I'm just freehand sketching that, but this is the point of the lab today, is to actually hook it up and collect data and plot the data and see if this is what we get. In fact, we're asked to do it twice, and so I will change colors here, because the second time you're asked to put in a little more resistance. So since this peak current would be V over R, you see right here the magical frequency would be when these two exactly equaled each other, then you would just have V over R, and that would be your most current you would ever get. And so that's why we call this a velocity selector, because it is getting the, well, if it was a bunch of frequencies, maybe I should put it that way, coming into this circuit, the only one that would come out, or the one that would come out the most, is the one right at that magical frequency. And hence the name frequency selector. Okay, I'm mixing it with our velocity selectors of our electric and magnetism. All right, so just to see this in action, you're asked to do it a second time with a higher resistance, and it's quite a bit higher. And what we'll see is that higher resistance not only brings down the peak, but it also widens out it. And so it becomes less of what we would call the quality of the resonator. And so if you really wanted to get just a narrow window of frequency, you have a low resistance. You do the best you can. Well, that's what I want to measure. Now, I should talk about this magical frequency. This magical frequency, as we said in class, and I'll just repeat here, would be when the effect of the inductor equals the effect of the capacitor. In fact, just to recap what we did in the lecture, we said for high frequencies, the inductor would stop the current. So the inductor would have a big reactance. At low frequencies, the capacitor fills up. Remember, the capacitor will eventually fill up and oppose the current. So at low frequencies, the capacitor is the one doing the stopping. And so that's why there is this middle ground, this magical frequency, that it's not too high for this one and not too low for that one. And at just that rate, then it's almost, these two balance each other off, and that's what the math says, and it's just as if you had only a resistor. That is the magical frequency. That is what we're going to call the resonant frequency. And so it would be when these two are equal. So this would be when omega L equals 1 over omega C. And if we put a little math in here, we get then omega squared is 1 over LC, or omega is 1 over the square root of LC. Now, of course, omega is the angular frequency, so let me take this one step further and just talk about I'll call it the regular frequency, or sometimes it's called the linear frequency, or just the frequency, then would equal this 1 over the square root of LC. So the frequency would be related to this. And so let me box that, because I know the very last step of the lab, and I believe it step 12, yeah, says right here to go ahead and measure the inductance of our inductor, the capacitance of our capacitor, to get out your calculator and see what resonant frequency you calculate. And hopefully what we will get in that step 12 is the number that matches what we're about to measure, what is our resonant frequency, okay, once we hook it all up. Now, what we're going to do then is, let me come over here and play the same tricky game with our oscilloscopes that we did in the last two labs. And that is, we would like to measure then the voltage. And so let me put here kind of a box and just say, okay, I'm going to put the scope right here. And I will hook that to channel 1. And I'll say it again, the whole point of that one is so that I can keep an eye during the experiment that I'm always putting out 8 volts. Because I will tell you, as we hook up the equipment and as we change the knobs, the output voltage does change. And our goal is to see how the current changes because of the frequency, not because this changed. So we want to make sure that if this changes, which, and I will say it will change on us, okay, then we want to adjust it so we're always getting the 8. So there's nothing really to write down other than just to remember that I'm going to put my scope on channel 1. Our channel 1 is going to be hooked to the function generator, and I'm going to just keep an eye on it. And with the newer oscilloscope, we will just turn on the button to measure peak-to-peak voltage and just make sure it always says 8 volts, okay? So what we need to measure, and we're going to make a little chart that plots then the frequency, and we will just measure the regular linear frequency, not the angular frequency. Even though I've put a omega here, maybe I should have just said plot versus F, because that's really what we're going to do. And then that is the calculation for the magical F frequency. The resonant frequency is its fancy name. So we are going to measure a bunch of frequencies. And as we measure them, we want to know how much current we're getting. And there's the problem we run into with our oscilloscopes. And I'll say it like I did last two labs. Remember, oscilloscopes, they're great. They do a lot of great things, but they do not measure current, at least not measure them directly. So what we're going to do is then hook up right here channel 2 of our scope. And we're going to use channel 2 to measure the voltage. And maybe I'll just put voltage number 2. And then we'll take advantage of, and then of course we want to measure peak to peak, because if we then divide that by the resistance, we will get the current peak to peak. And that's what I'm trying to explain over here. This is what we want to then measure. We want to figure out what that is and plot it. Actually, maybe I should, because this is how I'll write it down, is I will do voltage peak to peak. That'll be my raw data. And then I will calculate the current peak to peak. So you should know then that the first time I run the experiment, I'm going to set the resistance at 10 ohms. Okay, and so maybe I'll even put the formula here. Voltage peak to peak divided by R, and the first time R is going to be set to 10. And so hopefully we will see something that looks like this, that it peaks at some value that will hopefully match our calculation. And then we will also go to a higher resistance. So this should be 10 ohms. And the second time we do it, we're asked to go to 100 ohms so that, again, we could see that this really flattens down and spreads out. Okay? And so let's see what happens. And I hope it doesn't sink too much. Otherwise our graph will be so small it'll look like a straight line here. But that seems like an awful lot. That's going to be 10 times smaller. But that's what the instructions say. So I was going to say maybe I want to keep an eye on that, but I'm going to let you do the plot. So I won't know how low it is until you guys start doing the plots and turning it in here. All right, so now let me come to the front here and hook everything up. And so begin. And I'll begin with, like we did last time, I think it was working well with me in front so you guys can see the oscilloscope and the equipment. And then the data, I'll just write down here so I don't have to keep running back to the board. And so I'll just put here, okay, resistance of 10 ohms for this first setting. And so here is the decade box. Let me just check that all these resistors are at 0. Okay, they're at 0, and then let me just click the times 10 to 1, and so that's the 10 ohms. Okay, so I got my 10 ohms. And let me just make that chart then. I'm going to then put frequency in this column. And then I am going to measure the peak to peak voltage on channel 2. And so then I'm going to get with a calculation, and that's probably what I'll leave to you. You can just divide by 10 and get the current, although I will write it as a little formula, peak to peak divided by 10, so you can kind of set up in graphical analysis this column. Okay, and so in terms of units, this is going to be hertz, this is going to be measured in volts, and so this will be measured in ohms. Okay, and what you're going to plot again is the frequency on the horizontal axis and the current on the vertical axis. Oh, shoot. Thank you, Ron. Why did I say ohms there? The current will be in amps. Yes. Amps, volts. Yeah. Oh, well, ohms for the resistance down here. Yeah, that's what I was thinking. Ohms down here. 10 ohms, and then the current for the chart is amps. Okay, so with that in mind, let's go ahead and give it a shot here. Let me turn on my signal generator. Right now I'll just blast it to a full amplitude, and like I said, we're going to adjust this knob to make sure we're always at 8 volts peak to peak. Okay, so if I grab some wires here and follow that chart up here, it says take the signal generator and first go to our inductor. And we'll just use this for our inductor. You might remember it from the couple of the labs, but last lab we used it for Faraday's law. And I know I said a couple, but I think that's the only time we use this one for this class. Okay, but I'm going to feed it into here. And so this will act as my inductor because it's some good conducting copper, doesn't have much resistance, and it's got about 500 ohms in here. Okay. Then following that chart, it says go from the inductor to the capacitor. And I'll feed it into this big capacitor, which says on the side of it 1 microfarad, and we'll eventually measure it. So don't take that as exactly the number, but that's going to be pretty close to what we get. Then we'll feed it from the capacitor to the 10 ohm resistor, and then from the 10 ohm resistor we complete the circuit. So there's my AC LCR circuit. Okay. All right. So now, as we said on that chart, it would be nice to hook channel 1 of our scope. Okay, so here's our scope. This is why we did the last 2 labs, actually 2 labs ago, we did the how do you use an oscilloscope, and we had the older scope. Then we switched to the newer one last lab, and we'll wrap it up this semester with the newer scope. Makes things a little bit easier to measure. But let me hook up channel 1. And so channel 1 is in the gold. All right, so I have just channel 1 on. I don't know why I'm messing with it. I eventually want them both on there. I don't know why. Okay, anyways, but the channel 1 is in the gold. Okay. And so there is my gold pattern, if you will, just to kind of give you an idea. It's saying right now that there's 2 volts per division, and it looks like it goes up about 2 divisions, so it's going 4 up and 4 down. Okay, so that's roughly about 8 peak to peak. Okay, now so I can measure it, let me turn on the measuring menu. Let me go to channel 1, and if I scroll down here, see it says peak to peak, and I can just kind of push this in and select it. Okay, and so like I mentioned, really nice that we got these digital scopes. A little sophisticated in all the buttons that they have, but really nice for at least you can kind of see them. All right, now you'll see that the computer is then saying the peak to peak voltage is 8.24 right now. So I'm a little bit on the high side. And if I turn this knob here, you'll see it on the screen go down, and the measurement now says 7.2. So now I'm a little too low. I'm not ready to take a measurement, so I won't worry about exactly right now, but that's what I'm going to adjust here. And I'll say it again, every time make sure channel 1 is giving me 8 volts, so that as we see changes, it's changes because of the frequency, not changes because of the voltage from the source. Okay, now also channel 2. So here's channel 2, and I think that wire over there is kind of short. Let me get a little longer one here. But as I was trying to show there on the diagram, channel 2 is going to be looking at the voltage across the resistor, which we will use then to convert into a current. And so I will put channel 2 there. And so now I got a mess of wires, but that's why I wanted to set it up in front of you so you can kind of see what I did. I hooked up the series LRC circuit, and then I also hooked up my measuring devices last. Not that you have to, but I've said it many times, it's a personal trait that I like that keeps things straight. And so I'm trying to pass that on to you, okay? I've got what I measured. I want to build that first. Then I come in with my measuring devices, okay? Now, this one, I think I need to turn channel 2 back on. There it is. And maybe you can see the little squiggle of channel 2. Now channel 2 is set for 5 volts per division. You can see that in the blue. Let me change it so maybe you can see it a little bit better. Maybe I'll even go a little bit more. How's that? What if I did channel 1? a little bit more. Yeah, I'll just take that. Wait. I like channel 1 there, and maybe channel 2 there. Okay, so again, channel 2, it looks like it's saying 1 volt per division. So it looks like channel 2 goes up about 1 division, so that's 1 volt. And remember, divided by 10 ohms, so that would be 0.1 amp. Okay, so it's what I'd be getting right now. Okay, now, before I even begin my measurements, let me show you something kind of cool here. You will see that in this setting right now, the voltage and the current are peaking at about the same time on this display. Maybe not exactly, but pretty close. So remember what we said, that when you have a high frequency, the circuit is being dominated by the inductor. That's the E line. Okay? When you are at a low frequency, and I'm comparing my high and low to that magical resonant frequency. Okay, so when I'm at that low frequency, the circuit is being dominated by the capacitor. That's the ice. And so we would see current before we see voltage for that scenario. And when they about balance each other, they're in phase. So what I see on the screen right now would tell me that I am probably very close to the resonant frequency. I can measure it a little more accurate, and I will here in a moment. But if I just look at the number, it says 512 on my scope, and it also says 512 on my signal generator. So I have a good idea that the magical or the resonant frequency is about 512. Maybe a little higher or a little lower. It's kind of hard to tell if those peaks are exactly aligned. In fact, to me, it doesn't look like they're exactly aligned. They're a little bit off, and we'll check that out. But watch this. Watch what happens when I change this to a high frequency. Now maybe I'll lower channel 1 a little bit. Maybe I'll even increase channel 2 a little bit. But do you see for sure now the gold and the blue graphs here do not line up? Clearly, the peak of the gold one, which is the voltage, comes a little bit before the peak of the blue one, which is the current. Exactly. Because as we said, for these high frequencies, and so we're at about 700 right now, for these high frequencies, you are going to get this circuit to behave and act and look like more like the inductor. It's almost as if the capacitor's not even there. Sometimes we even use that phrase, capacitors are AC short circuits. That if you get to a high frequency, then you could just kind of ignore the capacitor in the circuit. And so the capacitors, get rid of or stop the low frequencies and let pass through the high frequencies. Anyways, but I wanted you to see before we got started this Eli effect, that the voltage then, or the EMF E, is becoming before the I in the L, the inductor. So there's our Eli. Okay. Now watch the ice effect. The ice is what you would see when the capacitor is dominating. So let's go to low frequencies. So, and again, my definition of low is frequencies that are below, and maybe quite a bit below, the resonant. So I'm going to turn it down to about a frequency of 331. And if you take a look here, you'll see that again, they don't match up. And again, the blue one this time matches or peaks before the gold. And so in this case, I have current before I have voltage or EMF. And so that's the I before the E with the C in the middle. So there's my ice. And so you see both of those. And it's kind of fun, and I'll kind of stand this way so maybe you can kind of see the scope. But if I increase the frequency, what you'll see see how that blue one is getting closer to peaking with the gold one, and at the same time it's getting bigger. And so right about there is probably my resonance. That's where not only does the blue one line up with the gold one, but it's the biggest. And then if I continue on for higher frequencies, you'll see now how the blue one gets smaller, and then the blue one lags behind the gold one. Okay? All right, so let me put it back and we can begin to take our data to what is probably really close to the resonant frequency. And let me circle around to the board. Here's kind of the tricky part of this lab is we'd like to get one measurement to be this value. So I'm going to start there. I'm going to try to find what that value is, and then move slowly left and right. And then when I get far away, then I'll make bigger steps, and then we'll plot it all. Okay? So if you were face to face with me, this is what I'd say. I'd say find the resonant frequency first. And once you find that, then make your measurements at about 10 hertz from each direction. And do that for a while. Once you get, as you'll see, about 100 hertz each way, it kind of flattens out and we can go kind of quickly. Actually, I'll probably go in steps of 10 for maybe 5 in each direction, and then I'll probably go a little more, like steps of 20, and then I'll finally just go steps of 100. So we'll have a good pattern here. All right, so let me find with accuracy that resonant frequency. Now you can see from the graph itself, or the scope itself, that it's got to be somewhere close to this 512. But let's now switch our scope, and I'll just remind you of those Elisaju figures. In fact, maybe I'll put it mathematically on the board. The easiest Elisaju figure was the 1-to-1. And since on channel 1 we're measuring the voltage, and on channel 2 we're measuring the current, those happen at the same frequency. So we're not doing any of those harder Elisaju figures. We're doing the simple 1-to-1. But if you remember me talking about this, if channel 1 was something like sine omega t, and channel 2 had the same frequency, but maybe out of phase, and especially if it was a cosine, if it's a cosine, you would start then, if this is the x-axis and this is the y-axis, and if this is a cosine, you would start at its maximum when the x-axis is at a 0, and you would get something that looks like a circle or an oval. Okay? But if they are in phase, and there's no difference between them, then they would each start at 0, they would each go up, they would each peak at their maximum, then they would go back and go negative, and you'd get a nice straight line. And that's really easy to see with your eyes. And so we're going to take advantage of the Elisaju figures that we did 2 weeks ago and find out when the XY mode becomes a nice straight line. All right, so like I said, I'm probably close but not perfect. Let me switch this into an XY mode. And for this model, you do it under the display utility, and you can actually then see right here where it says the format, and I want to go to XY and push it in. Nice. And I think you can see a little bit of an oval. And so that would tell me I'm not exactly at the right frequency. Let me try to give a different setting for left and right. Okay, good. So let me adjust the frequency and keep looking at the screen. I'm going to go higher for a moment, see what happens. Oh, and it got worse. Higher still. It gets worse. So I'm going the wrong direction. They are more out of phase this way. Remember, they're in phase when they're at that magical frequency. And I obviously went away from it. It became more of an oval, not more of a line. And so it's beginning to be a little bit more like the difference between a sine and a cosine. In fact, for high frequencies, I should get, very oval. But let me go back and use this then, a Lissajous figure, to find out what is the resonant frequency. So that looks like a nice straight line, and it looks like the resonant frequency is about 515. So I'm going to put maybe partway down my page, depending on, let's see, maybe about halfway down my page, 515. That's going to be my first measurement. Okay, so knowing that, let me go back and then go to my YT setting. Looks like it zoomed in a little bit. In fact, you can even see how perfect those peaks match up, the gold and the blue. Let me change the time setting. I'd like to see a couple waves on there. All right, and so there's my gold and my blue. Let me then make this measurement, but let me warn you, I want to make sure channel 1 is set for 8 volts, because I don't think it was. So channel 1 says 7.36. So I'm going to up it to 8, or depending on how finicky it is, near 8. I saw an 8, now I see an 8 again, and then it drops down to 7.92, so it looks like the digital converter is not giving me anything in between. So I'm going to call that 8 volts, all right? So I'll say it again. Don't take any measurement unless that peak to peak is at 8. And so now that it says here channel 1 peak to peak is at 8, I can just come over here to measure, and it doesn't look like I turned it on yet, measure. Let me go to channel 2. Let me scroll down to where it says peak to peak and select it. And it'll display it right down here at the bottom. And it says peak to peak is, what does that say? 2.72. Okay? And so there's my first reading, and now let's continue on. Oh, I bumped it again. Still got sound on you, Ron? Yeah. Sound okay?
It's fine.
Yeah, okay. And then let me go ahead and change it just a little bit. Maybe I'll go a little higher, and so I'll just do a little twist. How about right there? Give it a second to recount. That was not much of a change. All right, let me do a little more. Kind of get a feel for it. Oh, that's probably more than I wanted to do. I just wanted to go to about a 525-ish. And this will be the harder of the settings. It looks like there's a little bit of lag in it, bummer. So once I go backwards, I'm not changing anything. I'll take that one. 535. Okay, so let's go with 535. And then let me just check my voltage, because remember it was going to change. See, it went up to 9 and change. Okay, so I'm going to lower it down. And that looks good there. And so I'll call that an 8, and that's 2.26. So 2.26. All right, let me Do a little bit of a change and let it readjust. Oh yeah, now I got the hysteresis, so I'm going to have to do a couple little settings. See how that goes. Oh, that would be good if it was 555. That'd be another 20 in there. All right, good. So let's call this 555. Again, let's check our voltage. See, it changed. It went up to 10. Okay, so let me adjust the voltage, because again, we want to see the current change, but the whole point here is to see the current changes because we're at a different frequency, not because the voltage changed. And of course, both of those do affect it. And so that's why I need to keep, and like I said, sadly this changes its voltage because of the internal resistance inside of it. Okay, so this says 8, good, and now I can take a measurement of 1.60, 1.60. So you can see how quickly it's dropping, right? Look at that. It's already dropped quite a bit. All right, so let me do a little bit more. I did a little more than I'd like to, but I don't want to go backward, so let's call that what it is, 888. So 588. Again, got to adjust the voltage. Make sure that, again, we're seeing the effect due to the frequency change, not the voltage change of the machine as it changes because we changed the dial to a new frequency. Okay, so this is 8 volts and this says 1.02. Okay, let me go to a little bit higher. That looks like a decent change, and that says 607. So 607 is the next frequency, and I'm sure I will have to adjust the voltage again. Oops. All right, so there's 8. And now we switched units to millivolts. So that's 880. So I'm going to write it, though, in volts. 0.88, because my chart's going to just always be in volts. All right, well, let's go a little bit higher. See what that gives me. That wasn't much of a change, and we are getting quite a bit off of resonance, so I think we can make some bigger changes. I was trying to keep it around 20, but I got 30 there and then another 20, so it was off for actually, that's about a 25 there. Okay, so anyways, that's 634 is the frequency. I'll do that one, and again, gonna have to adjust the voltage and give it a chance to measure. Okay, 8 volts, and then that is 700 milli. Okay. Turn the knob a little bit. And let's do 662. 662. Again, let's take a look at the voltage coming from channel 1. And I'll adjust it so it says 8, and then that says 600. So I'm not plotting it yet. In fact, I'm not even going to plot it. That's going to be your part of the lab. But I clearly am seeing it getting less and less. You know, I'm on the right-hand side of this resonance curve. It's dropping off here. All right, so I'll keep going. Let me just do another little piece there. I will go to 688, and I will adjust the voltage to 8 and get 520 milli. Okay, that angle's better. Okay, let me go to a little higher frequency. Maybe I'll make even a bigger change now. You can kind of see two things in the picture. You see how the gold is now leading the blue. That's good. And so we're at a high frequency. That is where Eli, the voltage, is leading the current. And it's getting kind of small, so I'm going to change the scale setting on the blue one and make it stand up a little bit so I can see it here. Okay, but it looks like at a frequency of 757. And got to adjust the voltage again, because again, every time I adjust that frequency, sadly, puts out a little different voltage. And so I got to make a little adjustment here so that, again, we are seeing the change in the current due to the change of the impedance, not because of the voltage change of our equipment. All right, so here I've got my 8 and I've got 384. 384 milli. Okay. And if I go a little higher here, I get 802. And I'm going to have to adjust the output voltage for, and so that says 8 and that says 320 at the moment. 320. And let's see where that one gives me. I'll make kind of a bigger step there. This is 883 for the frequency. And I'll have to adjust the voltage. And so there's the 8 volts, and there's the 0.288. And I believe the instructions say at some point you're going to get all that noise. In fact, there it picks up my lapel mic again, so maybe I should make sure I stand back. Really didn't even change the voltage that time. So this is 942, and we're getting a voltage of 240, going back and forth. I'll call it 48. And maybe one more before we go the other direction, because the instructions just say go up to about 1,000. When you start getting that much, there's so little current, it's hard to get anything accurate. And so here is 988 for that frequency, and the voltage needs to be turned down just a hair. So that says 8, and that says 240. Okay, well, like I said, you definitely saw how the high frequencies acting like an inductor. Higher the frequency, the lower the current, and the more that the voltage leads the current. So let's go to the other direction. Let me turn this back down to 515-ish. I'll even put a few more on the display here. And so let's see if I can get us back to this 515. So that's a little high. That's 538. Let me do a little bit of an adjustment and pause. There's 520. Could make a measurement there and squeeze it in, but I don't think there's any point. Let me just bump it a little bit. And take that one. All right, so I'll take one here at 503. 103. Or 54, I'll call it 3. And then also, of course, here's where we got to be careful. We want to get the voltage up to 8. Whoops, I went too far. And we're getting a lot of current again. So probably want to see it on the screen here. All right, so the voltage going in is 8, that's good. And then I'm getting 2.52. Nice. Okay, and so let's begin to go the other direction. All right, let's take this one, 400, ooh, and 75, almost a change of 30. And then, of course, let's check the voltage. And let's put this at 8 volts. There we go. So we've got our 8 volts, and we've got a 1.52. 1.52. And it's not symmetric. You can see that in the math, but I was concerned about that big of a step. But yeah, so be it. Well, I think we'll see the overall pattern. It's hard to get these change of frequencies too much. Maybe I'll try to do a smaller step here. About 447, and again, check the voltage. Change really quick on this left-hand side of our resonance curve. Okay, so that says 8. Actually, it's a hair more than 8. Okay, so there's 8, and I'm getting, I'll call it 1 volt. So 1.00 volts. Take another measurement. Looks like about a 421. And we'll look at the voltage. Oh. All right, there's 8. Oops, too far. So there's an 8, and there's a 720, and that's milli, so I'll put 0.72. Okay. Make a little turn. Maybe I'll increase that channel so I can see it's a little better. That seems like a good number. 398 for the frequency. And let's look at the voltage. And so 8 volts coming out. 8, and we've got like 560 milli. Okay. A little more turn here. And we will do, how about 359? And a little more adjustment to our voltage, 8 volts, and looks like 400.400. Okay, another little adjustment. Maybe even change the timing so I can see it a little better. I don't know, maybe even make channel 2, it's getting pretty noisy there. But let me take that at 325. And again, let me adjust the voltage to about 8. That says 8, and that says 324. 324. Nice. A little lower frequency. It's really picking up my mic there. Let me go to 302. And it good, stayed about 8, and I got a 2, should we call it a 76, 276. And I'll go a little more here. How about a 272? Check the voltage. It did go up just a hair. Move it down to 8, so a little under 8, and that's going to be a 240. 240. And I got room for 2 more, so maybe that'll be a good way to call it good for the first resistor. So let's go all the way down to a frequency of 213. I'm still at 8 volts, and that's 0.188. If I stand back. And then finally the last one. Why don't we go down to 169 hertz. And is it still at 8? Good. And we're looking at about 132. So 132. Yay! So if you guys can see all that, great. This is what you want to put into graphical analysis, and this would be your first of your 2 graphs that you're going to be turning in. Now let me just point out again, don't forget you're plotting this 3rd column, so make sure once you put these numbers into graphical analysis you do a new calculated column, which is just this number over here divided by 10, so you've got to move the decimal one. You can even do that in your head while you're typing it in, I suppose. But then plot this versus that, and then hopefully you'll see this peak, and you can just see the numbers that it's peaking there. All right, so with that said, let's run a second experiment so we can see what happens when the resistance changes. And as I was trying to point out, that should lower the peak and broaden it. And so those are our 2 comparisons. So now let's run this with a resistance of 100. And so 100 ohms. And so let's go ahead and have this first column our frequency again. And we're going to try to get at that 515 and do the same thing. We'll measure forward and back. It won't be quite so peak, if you will, so I don't think we have to be quite as nitpicky as the small steps near the resonance, but we'll follow the same pattern. And of course we will measure the peak to peak voltage, and we will then get the peak to peak current by taking that peak to peak voltage, of course this time dividing by 100 ohms. And so this would be in units of amps, this would be in units of volts, and this would be in units of hertz. And let me kind of find, here was my good place to do my 515. And I will get close to 515. And so I'll come over to here. Oh, I didn't change my resistance. So let's see, let me go 100 and 0. All right, so there's the change of my resistance. Let me look at my dial. Let me come over here to about 515. Now, there we go. All right, and I guess I could switch it back to the XY setting, but I think I got it, 516. All right, and so again, we should probably make some adjustments, and in this case, I will spread out the time base so they don't look quite so crowded, and I'll lower channel 2 so I can see both of them. And you can see they look in phase, maybe not exactly, but pretty darn close. And same idea, that we should only make our measurements when the peak-to-peak voltage is at 8. So, oops, I went too far. And so there is my 8, okay. And so I am at a frequency of 515, 15 or 16, goes back and forth here. And I'm getting a peak-to-peak voltage of 6.44. Now that doesn't mean more current, by the way, because remember I'm dividing by 100, so it'd be 0.06. That's actually less than over here of 0.2. But the number on the voltage makes it almost look like we're getting something bigger with more resistance, and we're not. More voltage, perhaps, you might say, but not as much current. And that's what we're focusing on, the current we're getting. So more resistance should be less current, and sure enough, that'll come out that way once I divide by 100, because that'll be 0.0644, whereas this one, when I divided by 10, was 0.272. Yep. Okay. So with that in mind, let me go up in frequency. And so I will turn it just a little bit, and I think that's going to have kind of that gearing effect, so nothing's going to happen because I was turning it down. And so let me just go up a little bit and do that one. So that is 538, somewhat close to the 535. Let me adjust the voltage. This might not have much of an effect. Great. It might be a little easier this time because it's still at 8, and I get a 6.40. So there was a small change. That would tell me it's more level than a flat line at the top of a, instead of a top of a hill, it's, well, top of a prairie. I don't know there. Okay, a little mound out there. Okay, let me go up to another frequency, and that looks like a good one. The voltage did change as I went all the way up to 590. So let me lower it here. And I won't do quite as many data points because, again, as you'll see, they're not as critical. You'll get that nice flat with the mound in it, you know. So we'll want to see that mound. So at 590 and a voltage of 8, we've got a 536. I'll go to a little higher. Check the voltage on channel 1. So there it is at 8 volts, and I get a 496. 4.96 and 610. Okay. Let me go to a little bit higher. Let me just check the voltage. So I need to adjust it to 8 volts. So it says 8 volts. That says 436. 436 when I'm at a frequency of 643. And I'll go a little bit higher. Check the voltage. And it's changing more than I was hoping it would. I got to adjust it each time, except for that first time, 8. And then this is a 392. So 392 at a frequency of 668. Go another little click, if you will. Now that looks like a frequency of 683. That's not much of a change. Voltage did change a hair. Let me try to turn it down a hair. So there's 8, and there is 368. 368. Okay. Actually, it's a little under an 8. Maybe that will be a blessing here on the next little twist. All right. So that's looking like a good one. We are at 716. Well, we are a little over 8. Turn it down to 8, and that's a 336. 336. By the way, I'll just point out, I'll spread out the time. Again, we see the gold one before the blue one. So we see voltage before the current, as we should for the high frequency, because it's the Eli. It's acting like an inductor here. Okay. And I'll crank up the frequency yet again. Adjust the output voltage yet again, and get a voltage of 296. So 2.96 at a frequency of 752. And not sure how many more I should do. Maybe 2 more here. Let's call this 806. Let's check the output voltage. So there's 8 and 2.60. And so you can see it tapering down. It is a little mound here. And one more turn here, kind of a fairly big turn. Check the voltage. Oops, too much. There's 8. And so 8 or a hair under 8. And it's 212 and a frequency of 892. So that's the high frequencies, the ones above, high above resonance. Let's go the other direction again. And let's get it near the 515. Okay, so that's a little bit on the high side. They're still above 515. And maybe that's a good measurement going down. Ah, nice. So let's do 507. So going down in frequencies, let's do 507. And again, we want to make sure our voltage is at 8. I had turned it way up while I was adjusting it just to make sure it would stay high. All right, and so there's an 8 or a little 8 and 6.4. So 6.40. Yep, just a little bit of drop. Actually, the same drop the other direction there. Okay, and maybe I'll tighten it up. But you can see they're in phase again. We're back to resonance. Okay, so I will go ahead and make a small adjustments. Check my voltage. Whoops, too much. Get it near 8 again. And so I got a frequency of 482. And I get a voltage of 8, and that's 6.12. 6.12. Okay. A little bit of a change. I don't think I actually moved it. But we try that. Yeah, why not? I didn't move it by very much, but we'll take it in there. It's a 72 or 472. Change it very little. I still got 8, and then that's 596. So let's go to here. And so this will be 455 hertz. And again, careful adjustment. Make sure. 8 volts getting into our circuit, and it's 5.52. And another little adjustment. And we're going to have a little adjustment on the voltage. Always making sure it's at 8. All right, so there's 8, and there is 4.60 at a frequency of 422. Nice. Let's change the frequency, adjust voltage till it reads 8. So it reads 8, and we are at 356. So 356 at a frequency of 381. Okay, and another adjustment to the frequency, and then also another adjustment to the voltage just to make sure. We're always at 8 and 264, 2.64 at a frequency of 332. And another little adjustment to the, ooh, bumped that a lot. So be it, we're way off there. Okay, and maybe I'll even change the time scale there, but I really need to check the voltage. Make sure I turn it down to 8 volts. Okay, 8 volts, 192. So 192 at a frequency of 270, we'll call it a 6 hertz. A little more. Just the voltage. Really doesn't take much change. There we go. 156, or actually 1.56 at a frequency of 239. And I'll just do one more, even though we can probably fit 2, but I'll just make one more quick adjustment here and adjust the voltage to 8. And we get 1.12 at a frequency of 190. And I'll hold this up so you can kind of see it a little better. But there it is. Type these into Graphical Analysis. Get the current by taking this column and dividing it by 100. And then plot this versus that. And then hopefully you'll see, and hopefully what you will see when you plot this third column versus the first column is for, you know, this one, you'll see something that's kind of flat, but still has a rolling peak to it, whereas this one will be more hopefully peaking up and coming down. And whoops, actually it's steeper on this side than that side, so my drawing was actually the reverse of probably what you see. And it's not symmetric, so that's the idea. Now I think there's one more thing. Let me come back to the instructions, because I think I covered everything. For the example, on step 3 it says write the frequency in your lab report of the resonance. That was that 515 we saw. Then of course it says describe in your graph whether the oval or a line is the appropriate to find the resonance. So hopefully you're going to say line there. Another highlighted point here is make sure you're always at 8 volts. We were good at that. But here's the big one here. So finally we're getting graphical analysis. Plot the current versus the frequency. Did that. Then step 9 says repeat all of this for 100 ohms. Good. I did all of that. And then of course it says print your set of data and include this in your lab report. And doesn't say it, but then that means turn that in as a PDF into Canvas. Okay. So finally we get to this last step 12. It says, and it goes back to this equation. It says get out your meter and measure the inductance and the capacitance and do this calculation and see what you calculate for the resonant frequency. And so I will measure then the inductance of this circuit and the capacitance. And maybe I will write that on page 3. So what is L for this circuit? What is C for this circuit? All right, well, so to do that, maybe I will power down my equipment, and maybe the first thing I will do is grab my inductor. And I guess I'll need a couple of wires to measure it, okay? And I will grab the LCR meter. I think the only time we used this was way back when we were doing capacitors. And I said that it's in the off position. If you click it all the way over to the LCR, that's why it's called an LCR meter, L for inductance, C for capacitance, and R for resistance. And by the way, this one here is to test D for diodes, which we've had somewhat of an introduction to diodes not the last one, the one before, where we learned about the oscilloscope, and that was that step 3 where we turned an AC voltage into a DC and how a diode worked kind of as a valve. So I'm going to put it over here because it's measuring L, C, and R. And then as I look at this third of the dial says measure capacitance, this third of the dial says measure inductance, and this third says measure resistance. So I guess I want it down here. This says this is the maximum. Not sure how big this inductor is. So I'm just going to set it here for 20 millihenries. And that means it can read up to 20 millihenries. I don't think it'll be that big, but let's see what we get. Oh, we do get overload. So, oops, I went the wrong way. There's a reading up to 200 millihenries, and we get a number. So we get a number that definitely is bigger than that first setting I had, 20 millihenries. So we're looking at about 95.8. So 95.8 millihenries, or 0.0958 henries. Okay, so there's the inductance. Now let me take the meter and switch it over to the capacitor. And so I'm now going to read it as a capacitor. Notice I don't need to change this. The setting says that you can measure the inductance, capacitor, or resistance because it knows which third of the dial you were on. Let me grab the capacitor and say, all right, let me just make sure I got a good connection. And I know this one says on the side 1 microfarad, so I know it's close to that. So I'm going to put the setting at a maximum reading of 2 microfarads and see what it gives me. And it looks like it gives me a 0.983 microfarads. Okay? And so those are your 2 values. And I will leave it to you then. Maybe that off there. I will leave it to you to go ahead and put it into that calculation and then finish up the lab with step 12, which it says do the calculation, write down your results, and does it closely agree with what we measured? Remembering we measured 515. All right, well, we're done with the last lab. Congratulations. I know lots going on in your life besides school, but school's probably really big right now as everything's wrapping it up. I know that in a face-to-face setting, this is the time where things are just hectic because all these classes, the math class, the physics class, the computer science class, the chemistry class, everything's getting to the hard stuff. Everything's cramming in at the last moment. We've got the holidays. We've got tests followed by finals. So hang in there. There's light at the end of the tunnel. That's one thing neat, I think, about a school system is no matter how hectic it gets, no matter how little sleep you get, because you see the end coming and you're young and strong, you can kind of work through that. All right, bye now, and we'll see you later.